בפולסאות פרמטרים. בגלל שיש את הגשר הזה בין שעות רק עם הצפנות. אז ממש כאילו, צפון.
תראה, 7 דקות איחור? באיחור שם, כן.
כן, עכשיו.
חבר'ה.
אלכס, אתה רוצה לרשום או שאני משלישית?
אני יכול גם להתחיל, אבל...
מה זה?
אני יכול גם להתחיל,
לא משנה.
זה רק.
אולי גם נביא את זה שלו?
אני לא אמרתי.
לא.
אבל יש אמור להיות, פעם שעברה היה לו.
יש לך פוינטר?
פוינטר. לא, אותי יש אני אבין.
Oh, great. Yes.
אני לכם נוכחות, ובאתי ליהנות מהסרט. לא הייתי פה הרבה זמן. כל הפסח וזה.
אני יכול לבדוק לך עם הטיפ שלך?
איפה?
איפה נראה בגלל?
לא, נראה לי שואל אצל אמיר. אמיר, איפה תחזר? כמה שנים?
אני בדיוק לא. טוב.
תודה.
Alright, welcome. Alright, so I'm going to present a very recent paper from Nature called Epidermal Merkel Cells or Mechanosensory Cells, the two mammalian touch receptors. So let's break it down. We here have a piece of the skin. Piece of the skin. This is the dermis, this is the epidermis, and here you see a zoom in, and these are the Merkel cells that we're going to talk about. These are the nerve mammalian touch receptors that they are supposedly tune and change their activity. And what we know about them today, or think we do, that the Merkel cells, I'm going to call them NCs because it's easier, they express ion channels, they express neurotransmitters, but we're not really sure when exactly they release them, what happens when they do. They have kind of like contact with the slowly adaptive type 1 afferents. But again, and they're called together the Merkel cell neuron complex, but we're not sure exactly what exactly happens, what is the role of each part of this complex. And we know that these afferents are localized to skin regions that have high tactile acuity, and we call these regions touch zones, if I understand correctly what a touch zone is. Right. So we're left with some unanswered questions that they're going to try to answer. The major question is, what is the role of the Merkel cells in touch perception? And they're going to divide it into sub-questions in order to approach it more easily. The first one, are they touch activated? When we touch the skin or when we touch the Merkel cell, will it be active? And when it is active, is activating them enough to excite the afferent? And on the contrary, is silencing them is it gonna disturb the normal activity of the afferent? And if these two things happen, we can say that the Merkel cells actually tune the afferent activity. Alright, so we're gonna follow these answers and answer them in order. The first question is, are they touch activated? In order to answer this question, what they did, they used mice, first of all. They purified Merkel cells, dissociated them from the skin, and you can see here with the simulation. So they put an electrode on the Merkel cell, and they probed it with a glass probe, which is pretty small, and they just touched it, what they call displacement. So different sizes of displacement, and they found a pretty interesting result. The bigger the displacement, the stronger the inward current. So here we have different sizes or different lengths of displacement, so that means you just push further into the cell, and that causes different sizes or intensities of inward currents. Here in the red is the average. On the right, the next graph is just 6 typical cells, and the relationship that they show between the size of the displacement and the peak of the current. Alright, that's pretty cool. And so the next thing is to just characterize these currents a little more. What they did is they held the cells at different voltages using voltage sensing, and then created a mechanical simulation and measured the peak current. So we can get a graph of the voltage current relationship. And we can see from this result and the previous results that the current properties are it has fast activation or fast gating mechanisms. It has a linear current pulse relationship, and that is indicating of a non-rectifying, non-selective ion channel. Interestingly, this is concordant with channels that are mechanosensitive, that are mechanoreceptors, and they are encoded by piezo genes. So in order to know if these cells actually do have those piezo genes, and it's not just some, hypothesis, we should do what? You should know by now, qPCR, right? Reverse transcription, which is what we're doing in the lab. So they did that, and indeed we see that they do express piezo1 and piezo2 genes. So let me just read you through it. These two genes are genes that are expressed in the keratinocytes, and that's the majority of the cells in the epidermis, and just regular skin cells. These two are the genes of interest, I think. And the ATO1 is a gene that we'll encounter again later, and it is very essential for the formation of Merkel cells. So obviously they express it substantially more than actually not significantly more, but more than the total epidermis, and we can see that the Merkel cells do express piezo genes, but only the piezo2 is significantly higher than the rest of the cells in the epidermis, and this might have, so that means maybe it has, the piezo2 channel is functionally important for the function of the cell, and we'll touch that a little bit later. Yes, I was going to say, if you have questions.
What is the ATOH1?
ATOH1 is a gene that encodes a protein that is essential for the formation of Merkel cells. Later we'll see that when you knock out this gene, you just don't have any Merkel cells. Okay. Alright, what we've established so far is that Merkel cells are indeed touch sensitive, meaning when they come to touch, they will produce currents, and they don't need neurons to do so. Alright, next step, we want to know if they can tune the afferent, meaning if I activate the Merkel cells, will I get activity or action potential in the afferent? So the natural way to do it is, of course, optogenetics. So they created mice that express channel rhodopsin only in the Merkel cells in the epidermis. They actually express it in other cells in other places, but in the epidermis it's only in the Merkel cells. And we can see here, alright, so we have a few pretty images. The first one is, these are Merkel cells expressing channel rhodopsin. It's a confocal image, and this is what a touch dome looks like. It's just a piece of area that has a very high sensitive to touch. Next image is immunostaining, and you can see here that these are Merkel cells expressing channel rhodopsin, and these are the afferents, and it's very visible do not suppress channel adopting. Yes, can I help you? No? Okay. And the last one, I think it's not as informative, but it's pretty. So we have, this is an image taken during the recording. They use different filters to image the light stimulus and the channel adopting, and you can see that they stimulate the right areas. And they tried different areas just for control, but all right. So what they actually did is they took a piece of mouse skin, and while stimulating with blue light the Merkel cells, they measured from the afferents. Alright? What they did, what we see here, are 5-second light pulses in different intensities. Each blue bar here indicates light stimulus. And it's very, very visible, it's very, very clear that the light creates action potentials from the afferents that are in phase with the light stimulus. The last reaction here is in response to a mechanical stimulus. So you just touch the skin, you see that they create, at least visibly, what you can see by a very, very similar response. So they, of course, quantified this a little bit and tried to characterize the response. And you can see, first of all, that the frequency, the firing rate, was proportional to the light intensity. And the second thing they were interested in, they found that all of the afferents that responded to light were also activated by touch. And they wanted to make sure it comes from from single unit recording. So they did some spike sorting, some comparison of the spike waveform, and they found, you can see these are the spikes that are produced from light and from touch on top of each other, and you can see that it originates from the single unit spike. Right, so the next thing we're interested in, so we established that these afferents are activated when the Merkel cells are depolarized, but they wanted to make sure that this is the same type of pattern, same type of activity, that when you touch a skin and you get a certain maybe Merkel cell mediated response from the afferents, we get the same thing when we do it using light. So, what do we know about the touch-activated pattern? It has two phases. The first is the dynamic phase, which is high frequency at the onset of the stimulus. So right when you touch it, you get high frequency firing from the afferent. And the second part is the static phase. It's sustained firing throughout the stimulus. And they recreated a sustained stimulus, right? So you can see the blue light here it lasts 108 seconds approximately, and the black is the actual data, and here you can see that the firing rate is sustained throughout the whole stimulus. So we can see that the depolarization of Merkel cells is enough to get a robust static phase, it mimics the static phase of the touch-activated response, which is very cool. So what we've established so far, depolarization is sufficient for the activation of afferents. We still haven't, there are two things missing, or more than two, but two main things missing. First is the dynamic phase. Can we mimic the dynamic phase? And the second, we found it's sufficient, but is it necessary? Alright, so the next step is to silence the Merkel cells and see if it disrupts, if it's necessary for the normal activity. Okay? With me? So they did it using two approaches. The first is optogenetics, the next is knockout. So let's start with optogenetics. They made the Merkel cells express a pump, a hyperpolarizing pump that responds to green light. And what they did is they created mechanical stimulations, sustained mechanical stimulations, and during that they gave 10-second green light stimulus with 10-second intervals between them. So what we see here is a reduction in the touch lobe firing rate. You can see that whenever there is green light, there is much less response, and when you go further and further down the stimulus, the inhibition is bigger or stronger. And you can see it here quantified, that it is very, very significant, it's very robust, that when there is green light, the sustained phase, the static phase, is inhibited. So we know that depolarization is necessary for robust steady state firing, still missing the dynamic phase, right? So the next thing is to knock out some genes. They created, remember you asked about the ASO1, so though, it is necessary for the formation of the Merkel cell. So when you knock out this gene, what we get is an epidermis that has no Merkel cells, but it is innervated by the afferents. So it's interesting to see if the pattern of these afferents is different. So we will still feel touch, but maybe differently. All right. So this is what they did. They created, this is 3 types. The step line here is just 3 different intensities of a mechanical stimulus. The dashed line is the skin, so you can see it all pushed through the skin. And the gray bar signifies the border between the static phase and the dynamic phase. So it starts with the dynamic phase and goes through the static phase. And of course this is the knockout mice and this is the control mice. And it's already very clear that the knockout mice have very different patterns, if not weaker in pattern. It's just another way of looking at it using the firing frequency, measured at every moment. And again, you can see very clearly that there's almost no firing rate for the knockout mice, or very different anyway. So just more quantitatively again. So here we have the spike count. And you can see that the spike count and the firing rate decrease significantly for both the static phase and the dynamic phase when you compare SO1 knockout to the control. What we see here, first on the top, is the ISI is the mean, the inter-spike interval. So it's much longer for both phases for the knockout mice, which is, it means understand there's just a longer interval between spikes, which means the firing rate is lower, right? Just another way of showing it. Interestingly, if you remember the PSO2, which we suspected might be significant for the function, it creates a different type of response for the static phase, but it doesn't really affect the dynamic phase in a significant way. So we know that the Merkel cells tune the dynamic response of the afferents.
Is it PSO2 knockout?
Yes. So they do it in a way that is some mechanism that does not rely on the PSO2 expression. In other words, the touch-dome afferents respond to touch, but firing properties are distinct dramatically from the canonical slowly adaptive type 1 response. They actually categorize it as different afferents when it's missing Merkel cells. So what we've established so far in this part is that the depolarization of epidermal Merkel cells is necessary for the static and the dynamic phase firing in SA1 afferents. To conclude what we've established here in order, the MPs are touch sensitive, and their activity, they tune to very important features of the pattern activity of the slowly adaptive type 1 afferent, which is both the dynamic phase and the static phase, which probably signals different things. And I did feel myself, I was left with some questions. So first of all, they didn't describe the mechanism at all. They pointed out at the beginning that there's neurotransmitters and cells, but we're not really sure what part they play in this process. We just kind of jumped from the beginning to the end without understanding exactly what goes on. Second, everything was done in ex vivo and in vitro. It would be interesting, I think, to know if something happens. How does it happen in vivo? Just for open research. And last thing that bothered me, I didn't think they described the stimuli sufficiently, and the variants were only in the strength of the stimuli and not in different size. Maybe we would find different patterns of activity for different types of stimulus, for example, different textures, and not just, from what I understand, all of the stimulus were in certain angles towards the skin, and it would be interesting to get a variety of that.
This has any impact on their conclusions in your eyes?
Maybe the Merkel cells tune the afferent activity only in certain kinds of stimuli, and they do not mediate other kinds of stimuli. Maybe not, but it's not robust, I think, conclusion. It's not gonna make them wrong. But yeah, that's it.
photo.
Did they touch other cells to see if they depolarize? If the Merkel was depolarized or the
Like
other?
if we touch a neuron at different times, will that neuron fire?
In general, a neuron,
Yeah.
not necessarily. I mean, usually when we touch a neuron, we touch it, we move it, it doesn't spike
Okay.
just because we touch it. But these are specific type of neurons that are supposed to be sensitive to
Yeah, I
mechanical.
understand that, but they didn't. From what you said, they didn't use any control, so I don't know if it's the touching that really made the cell fire, not just
I mean,
some other.
they did.
I don't know, control for what? For touching other neurons and see if they fire?
I mean,
But if they will fire, this doesn't mean anything about this now.
They did, for example, the first.
it is a confound though, because if you're taking the cell out of its natural environment and you're eliciting some type of condition which is unnatural, and you think this mimics touch,
Yeah.
but you might be wrong.
What do you mean it mimics touch? You touch it.
You literally
Yeah,
touch it.
but you
How can you mimic
don't
touch?
touch it this way. Obviously, you touch like a specific cell. It might go through channels, not because of a specific mechanosensor, but just because you like scratch the
But
membrane.
then why would there be different, a very clear relationship between the size of the displacement and the current?
If I do a
Open
bigger
more?
scratch on my hand, I might bleed more. I don't know.
Yeah, but I understand, but I don't understand where are you taking that? In what sense? Say every cell in your skin that you touch is depolarizing. Then you want to say that this is non-specific, that there's nothing special about this neuron?
From what I understand, they're thinking that there is a specific receptor in these type of cells.
Yes.
And
They show that they have at least they have express the genes for this mechanoreceptor. So they have.
it seems weird that there's no control for that.
I'm actually not sure. I think they did other cells then. Maybe I'm wrong.
Maybe I have it here.
I think that they checked it with other epidermis cells that were not Merkel cells. The same type of histology.
Maybe.
But also when they inhibited the cells, they touched them and
Yeah.
they didn't fire, right? So
Fire them.
They told them.
Yeah, you have a control on the other side, which when you knock these cells out, you have change in your
No, I don't.
properties.
I'm not arguing with circuitry. That's obvious, probably true, but the the fact that this is a mechanosensor, I wasn't completely convinced from this
Okay.
result.
Does anybody know if there's a theory about how these mechanoreceptors are, what sort of molecules they are, or what sort of transducing mechanism is there that translates touch into current?
They were only discovered or published in 2011, if I'm not mistaken. So I think that's the first paper that actually uses the discovery of this piezo 1 and piezo 2. So it's very, very new. It will happen, but I don't think they crystallize them or anything more.
They didn't really bother with anything molecular, well, except for the first part.
Do they look at any group dynamic behaviors? So if you get touched in the center, how far does it radially spread out? Or
Not that I'm aware of.
Good question. Can you put one of the first slide on, not the first data set?
Where's the first data?
One more. One more.
There? Yeah.
Yeah. Anyone find something strange?
Which one?
Any pose?
Yeah, that's what was bothering me. The fact that you see it depolarizing, then you just see it going down. That's its baseline.
That's current, not voltage.
Yeah, but there is some residual voltage. So there is some adaptation, that's true. But still, look at the unit. The displacement is of 2 range of these of the cells is very, very limited, and it's kind of completely out, in a way, completely out of the bright range. It's like every blow of wind will completely saturate your sensor. So something here, I mean, this could completely be because of this unnatural condition, where there is no skin and fat or nothing that actually mechanically dampens the thing, but it's extremely, extremely sensitive.
But I mean, how, like, the relevant scale is probably, say, millimeters or centimeters, right? So
I mean,
how,
when we looked at that, we said, yeah, the relative displacement are.
So, but maybe the way they measure this displacement is how much the cell as a whole gets compressed, and then it would be the correct scale, right? If the diameter of the cell so much, something like 50 or 100 micrometers, then compressing it by 2 micrometers is maybe the correct scale, right?
No,
No, I'm not saying it's not the correct scale. I just mean that the dynamic range is very, 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 very narrow. So, like, the difference between moving the cell by 1 micron and 3 microns in real life seems like very, very strange. Like, you would expect this to be spread over a larger range. I would expect. I can, there are ways to deal with that by just having many cells and kind of distribute the population activity, which is what's actually being done, obviously. But still, it's very, very sensitive.
We don't know how, maybe it's not the correct term, but we don't know how rigid all the cells are, or how much compression of the skin here acts on this.
That's what I'm saying.
just one more second, the next slide. Yeah. Why do you say this linear relationship implies non-rectifying? That's rectifying.
So that's the definition of
That's
rectifying.
the definition. Rectifying is when there is either misdirection, when it's not linear. The definition. So it doesn't treat a certain range of voltage differently in the.
So if it's either rectifying or selective, then we mean non-linear?
Non-selective, I think it's just because of the reversal potential that indicates reversal potential is the potential.
Right. Oh.
Yeah. Cool.
One thing I want to say about this paper, it's kind of it's a bit strange. It's a paper in Nature, and it seems like almost kind of, what the hell, in like 2014 we have a paper in Nature that, touching the skin you get spikes in the appendix. It's a bit weird. But the truth of the matter is that all these manipulations that has been done here couldn't be done before we had access to the genetics and the optogenetics and all that. So there were hypothesized, based on anatomy, that these cells are activating the afferent, but no one could actually show that directly because there was no way to do that. So now they did it, but still, as Shai told you, they still completely skipped the whole process. We still don't know what exactly happened due to the touch. There's probably current going in. They're probably going
by O'Connor and others. Um, don't be afraid. You may have been wondering why we cannot tickle ourselves. So this is not part of the paper. So generally speaking, it has to do with the fact that our brain predicts the sensory consequences of our actions, and the tickling sensation is cancelled. But on the other hand, when someone else tickles us, and the same stimulus arrives out of phase, then tickling is perceived. And you're probably asking yourself, why am I telling you this? And this is because, so generally speaking, for animals and for humans, to perceive touch, sensory input must be integrated with relative timing of neuronal signals representing the input. And so, in this article, they mainly address the question of what is the underlying, or what are the underlying neural mechanisms that enable mice to determine the location of objects in their physical environment. And in order to answer this question, they used different techniques. So first they used behavioral object location discrimination task. Then they used in vivo electrophysiology and in vivo optogenetics. So we'll start by the behavioral experiment. So they trained head-fixed mice to determine, to perform object location discrimination task. And so in each trial, a vertical pole appeared in one of two locations, and the mouse had to detect where it appeared. And so this is the exact experimental, the schematic diagram. So first, please ignore the multiple whiskers that you see. So in this paper, in this experiment, mice had only one whisker, the C2 whisker. Also note that all experiments were performed in a dark room. So mice could not rely on their vision to detect the location of objects. And then, so the vertical pole appeared always on one side of the head. And then on each trial, it appeared in one of two different positions along the anterior-posterior direction. And the distance between these two positions was on the order of 4.3 millimeters. So very small distance. And also note that the pole was always, so regardless of the position of the pole, mice would always touch it with the whiskers. So it was within the whisker field, if you will. And so when the pole appeared more posteriorly, closer to the whisker, we refer to these trials as the go trials or the yes trials. And otherwise, it is the no-go or the no trials. And so the task was, during the exploration window of 2 seconds, mice had to use their whiskers and try to detect in which, whether the pole appeared on the yes location or the no location. And if it appeared on the yes location, mice had to lick in order to get a water reward. So more specifically, if it was yes location, they had to lick and they would get a drop of water. And the high-speed videography enabled the researchers to reconstruct the whisker movements and whisker touch on a very short time scale, on a millisecond time scale. So next they performed in vivo electrophysiology using the cell-attached patch clamp technique. So they recorded from layer 4 of the mouse barrel cortex, and more specifically, they recorded from in and around neurons in the C2 barrel, um, while the mice perform the object localization task. And so in this figure, we see the mean firing rate of 13 neurons in the C2 barrel, and the firing rates are presented as a function of time from first touch, which appears at t equals 0. And we can see that the neurons are rapidly excited by touch. The peak firing rates occur at around 10 milliseconds after the first touch. And so going back to the object location discrimination task, there are two plausible behavioral strategies that mice could use in order to detect object location. So first, they could deduce object location by the position of the whisker at the moment of touch. And second, they could deduce the object location by somehow estimating the forces acting on the whisker at the moment of touch. So presumably, if the object is located closer to the whisker, it will exert stronger forces on the whisker at touch. And these two behavioral strategies correspond to different neural codes, being spike timing and spike count. So spike timing simply means that, for example, if the object is located closer to the whisker, it will interact faster with the whisker, producing rapid spiking activity, as we've seen in the previous slide. And on the other hand, spike count means that if, again, the object is close to the whisker, it will interact more often with the whisker, simply producing more spikes. So it will interact more often and probably also more strongly with the whiskers, producing more spikes. So these are the two possible neural codes, and throughout the rest of the paper, they'll try to determine which neural code underlies object location discrimination. And so next thing they did is they asked whether it is possible sort of to fool the mice and to induce using optogenetics and illusory sensation touch and illusory perception of object location. And in order to achieve this, they selectively expressed CHR2, channelrhodopsin, in the C2 barrel, and they achieved it using Cre recombinase and the AAV virus. And they also created quite sophisticated experimental paradigms. They also created a virtual pole using infrared light, and they placed the virtual pole along the whisker. And whenever the whisker crossed the pole, a single light pulse was delivered. And we can see it here in the schematic diagram. So as I mentioned, so you can see the virtual pole and the sort of the normal tangible pole, and the virtual pole is placed along the whisker. And actually, they coupled this experiment with the initial object location discrimination task, and they used the virtual pole in a subset of trials. So every fourth trial, the virtual pole appeared. And in order to see whether they can fool the mice and induce an illusory sensation of touch, they concentrated on the no trial. And what they found is that they could actually fool the mice to quite a large extent. So in over 50% of the stimulated node trials, responses corresponded to the yes locations, meaning that the mice were fooled to quite quite large degree. And in order to further quantify the illusory sensational touch, they calculated what they call the Fulling index, which is the difference in yes response probabilities between stimulated and unstimulated node trials. And so going back to the neural code, if you remember, so we said that they hypothesized that mice use either spike count neural code or spike timing neural code in order to detect objects in the physical environment. And it seems that optogenetics is a very good way to test which neural code they in fact use. And what they did is that they varied delta t, and delta t is simply the time between the time difference between the whisper crossing the pole, and the virtual pole, and the photostimulation. And delta t varied between 0 to 50 milliseconds. And what they found is that there was no relationship whatsoever between the different values of delta t and the Fulling index. And we can see it in the following figure. So you can see indeed, to be honest, I'm not a big fan of this graph, but that's what they put. But in my opinion, it's really hard to see what's going on here. But without getting into too much detail, their conclusion was that the Fulling index, so the Fulling index is presented as a function of delta t, and so there's no relationship whatsoever between the Fulling index and delta t.
But was there a relationship between the delta t and the time of licking?
Time of?
Of the licking response?
What is the licking response? What do you mean?
Wouldn't they have the yes response when to which they lick something?
Yes. No, this they kept constant. So they didn't quantify this. So the exploration window was still 2 seconds.
But you're asking about the latency of the response, right? So if the shorter delta t leads to an earlier response.
Yeah.
I don't think they show this.
Okay.
Yeah. I don't think there was a relationship. So their conclusion from all this is that it seems that spike timing is not really predictive. It's not really underlying the behavioral actions of the mice in determining the object locations. And they proceeded to the second possibility, to the second neural code, and they checked whether manipulating the spike count has an effect on performance. And what they did, again, using optogenetics, they stimulated inhibitory GABAergic neurons in the C2 column, in the C2 barrel. So again, the C2 barrel is the barrel corresponding to the active C2 whisker. And so they stimulated the inhibitory GABAergic neurons during the exploration window. And this time it was done without the virtual pole, so back to the original setup. And so what they found is that there was an increased performance in the no trials, but significantly decreased performance in the yes trials. And you can see indeed that it is quite significant. So the lines, so for each case, the 3 lines, these are just 3 different mice, and we can see indeed quite significant changes in performance following optogenetic stimulation, both in the yes trials and in the no trials. Okay. And to conclude, so we saw in this paper that optogenetic stimulation in the barrel cortex could induce illusory sensation of touch and illusory perception of object location. And taking together the data from their experiment suggests that mice used spike count neural code rather than spike timing neural code in order to detect objects in their physical environment. And I think this sheds some light on the whisker system in general and on the ways mice determine object locations in the physical space. And so some thoughts. So on a personal note, I thought this paper was quite interesting. First of all, because of the many different techniques they use. So for example, so they relied heavily on optogenetics. And for example, speaking about optogenetics, we've seen previously one application of optogenetics where they induced illusory memory in the mouse hippocampus. Not illusory, they induced false memory in the mouse hippocampus. And this is quite similar but also different. It shows another application. And they could induce another sensory modality. They could induce illusory touch in the mouse barrel cortex. But one sort of suggestion or critique which I have regarding this paper is that some of the conditions they used are simply unnatural. So meaning that mice performed all behavioral experiments with one whisker. And so I think, please correct me if I'm wrong, but perhaps using one whisker, the brain learns to read out the activity from the relevant whisker, from the relevant barrel corresponding to the active whisker, and ignore other inputs from other barrels. But the question is, what happens if multiple whiskers interact? And how is their interaction in the real environment corresponds to mice detecting object location? And I think it's worthwhile checking it.
In what sense?
In what sense?
Yeah, I mean,
so maybe
first of all, how would you check?
Okay,
second,
it's harder,
can you give a reason why, say, if you have like three whiskers, do you think that the conclusion about timing versus count would change? And if so, why? Why do you think it would change?
So yeah,
I mean,
the question
no
is,
experiment is natural,
I
except the experiment that is coming next is a little bit more natural. But most experiments are not natural by definition. Starting from slicing the brain is very unnatural.
Yeah.
And having a head-fixed animal with one whisker is not natural. Obviously, especially if you put light into the brain. But the question is whether these things actually affect the conclusion. Because I mean, basically, without offense, this is something that came up in the previous paper, and you can write it down on every presentation of the paper from now till the end of the course next year. So every paper that you will present, the critic that it's an unnatural experiment is okay. The question is what in the unnaturality of the experiment can affect the conclusion.
So the question is, how are the different the answer is that I don't know how it would affect, but it seems that so if you combine so different input from different barrels as opposed to only dealing with one active barrel which is relevant to the active whisker, so the question is how they will interact.
Okay.
You mean something like relative timing between whiskers?
For example, yeah. So if you have, yeah. C-reactive virus or free or
And also one of the whiskers could be spike counting or spike intervals instead of spike counting. Maybe they just got a whisker that was
maybe they're lucky,
yeah.
That's
That was
Meaning
very
other
good.
whiskers will do it with spike timing and some whiskers with spike count.
So they dealt only with the C2 whisker,
Right.
but maybe yeah,
They just
there
were
is,
unlucky.
maybe there is a different operating mechanism in another whisker, or maybe completely different neural code underlying object detection.
So just by chance, I saw another paper that is, I think, more than 10 years old, and they just measured, so without optogenetics or anything, they just measured extracellularly in the barrel cortex and calculated correlations between spike times and object locations, and their conclusion was that 80% of the information about the object location is contained in the time of the first spike. It's not important now how they quantify this 80%, I think, but can you reinterpret this in view of the new paper, or is there a conclusion that goes well with both findings?
Okay, can you repeat it again? Yeah, I would like to be sure that I understand.
Can I just add a question? No, it's actually related to the same thing. Is for Mickey, were you convinced of the conclusion at all?
Well, personally, no.
Yeah.
But not because it's the honest shot. And
No, because the internal validity of the experiment is just nothing to do
no,
with it.
I actually want to comment on that in the sense of what Johannes just said. So the reason they actually went to do this experiment in some way is because this question of timing versus count is like the how would I say, the holy grail of neural coding. You probably noticed that already. That's one of the very fundamental questions that we try to understand what in the properties of spike trains convey the information about, the outside world, the inner world, whatever. The barrel system is indeed the system where the whisker, since you know the position and you can actually track the whisker, you can actually correlate very well the spikes, and you saw that the action of the neurons is very reliable. Every time there is a touch, there is a spike in layer 5, in layer 4 neurons. Not every time, but once there is a spike, it's pretty accurate in time. So people actually thought that the barrel cortex is using timing in order to encode information, which would not be completely surprising given that it's so close to the stimulus. I mean, the stimulus has some timing properties because you move the whiskers and you touch things, and this is going to be interpreted into spike timing. And the question indeed is whether the brain is using this information, yes or no. And the important point in this paper is that you can now, with optogenetics, manipulate the neurons causally and change the activity of the neurons and see if this has any effect. Now, they didn't do it 100% clear in this experiment, and I can tell you that they're working hard now to do it better, obviously, and in the future you will see things that will be in very in higher resolution, in the sense that you will not stimulate all the neurons in layer 4, but only specific neurons, and you will be able to stimulate them in different patterns of timing. But this is basically the idea behind this kind of experiment, that you can manipulate the timing of the spikes and see if you can change the behavior, if you can change the readout of the brain. So in that sense, it's a step in the right direction. It's not 100% convincing. I agree there are a lot of critical issues with this paper, but it's more like a demonstration of where this area of coding is going in order to answer this question. There are very detailed specific issues that I can go into, but since some of the things were not even presented, so I can't actually answer you. But you can ask love meeting and the same discussion.
Same one.
Similar discussion, yes. Okay.
Ten-minute break.
מה? גם הטפל תוך כדי מהשולחן מגילה מהשולחן.
זהו, זה בעיה לפה. זה לא נופל, זה לא נופל.
כמה שאני יודע זה אחד הענייני קור הכפר,
רק תתן לי שנייה הגדרה, אתה עושה את זה בתור מאסטר, בתור פרויקט, בתור...
כאילו, כן.
זה הרעיון למאסטר?
כן.
זה יכול עם יורם? חיים.
אוקיי, אז יש סתם, כאילו המוטיבציה, או אחד מהמוטיבציה, אבל...
זה של מי או שלך?
יש איזה מאמר שכתבתי על זה ב-2011, זה משהו שעובדים עליו, אני מניח שאתה מכיר את זה במדעי המחשב, זה אם יש לך איזשהו רנדום גרף, שיש לו איזה ג'נרטיב מודל כזה, והג'נרטיב מודל זה מין בלוק מודל כזה, יש לך לכל נוד בגרף יש לך לייבל, ויש לך איזה אינפיניטי מטריקס כזה שאומר לכל, יש לי להגיד 1000 גרפים 1000 נוד ו10 לייבל, ואז לכל זוג של נוד משני לייבל יש לי מטריקה כזה שאומרת מה ההסתברות שהם ימשוך, ואז ככה יש לי ריאליזציה של גרפים כאלה, ויש אלגוריתם שמדבר על הבמה, ושכאילו מריאליזציה אני עושה איזה מין לוג, מקסימום לוג לייקליהוד, וממנה כאילו מפיק את הפרמטרים של המודל, שזה כמה לייבל יש, מה הפרקציה של כל לייבל, וכאילו מה ההסתברויות של האינפיניטי מטריקס. ואחר כך גם, ועל זה גם אחר כך כאילו, מה גרופ אסיינמנט, אחרי שהפקתי את הפרמטרים האלה, אז אני יכול להגיד סטטיסטי, כאילו גם מה לייקליהוד של, כאילו מה לייבל כל... אוקיי, אז כאילו ההשלכה היה, כאילו אני מבקש שזה לנוח, אז כאילו יש לך, עכשיו יש לי קונקטור, כמובן נסו למידות, עכשיו יש לי, לא, עכשיו זה n שווה 10,000, ו-Q זה מספר הלייבל, לא זה שווה 7, נגיד, ועכשיו אם נותנים לי מפה, אני כאילו עושה איזה מין בלוק מודל כזה, ומשחזר כאילו את הסוגי תאים, כאילו מהמדידות האלה נותנים לי רק את המפה בלי הסוגי תאים. עכשיו, אבל...
רגע, מה זאת אומרת מהמדידות?
הם
נותנים לך גם את סוגי התאים בדרך כלל? להפך, אם כבר נותנים לך את סוגי התאים בוודאות הרבה יותר גבוהה מאשר שאני...
כן?
אני חושב,
אוקיי, אז בואו, אז אתה יודע מה, אז בואו נשים שנייה את המוטיבציה של קשר למשהו בצד, אבל רק על זה יש עוד, זה כאילו משהו יחסית, וגם מגלים שם שבמאמר הזה שיש שם מין מעבר, יש כאילו תחום פרמטרים שהוא כזה detectable, ויש תחום שהוא non-detectable, ויש גם detectable. יש שם איזה מין מעבר, מהריאליזציה אתה לא יכול, כי עושים איזה מין מודל כזה של פיזיקה סטטיסטית, כאילו זה שקול למינימיזציה של אנרגיה חופשית כזה, כאילו המקסימום הלוג לייקליהוד זה כמו מינימיזציה של אנרגיה חופשית, ואז זה נותן את הפרמטרים בהסתברות חיוב. ויש, אוקיי. עכשיו, על זה יש איזה איזון מסוים שבמקום לייבל, יהיה לך, לכל נורון, יהיה לך פיצ'ר וקטור כזה, שזה בהנחה נראה לי שזה מתאים שיש לך יותר לייבלס, או שזה יותר טבעי, כאילו להשתמש בפיצ'ר וקטור של לייבל. יש נגיד פיצ'ר וקטור בינארי כזה, לא יודע, מימד חשוב, אז במקום אינפיניטי מטריקס, כאילו זה די דומה, רק שזה מין סוג של איזון על הבלוק מודל.
אבל האינפיניטי מטריקס היא עכשיו כל הפיצ'ר?
היא עכשיו,
אוקיי,
אז נגיד לכל נוירון יהיה לו איזה, כאילו יהיה לו איזה Fi ו-Gj, כאילו פיצ'ר וקטור נגיד סינפטי ופוסט-סינפטי, ואז האינפיניטי מטריקס זה יהיה, כאילו המודל הכי פשוט זה יהיה זה כזה. משהו כאילו, זה יהיה סימטרי כאילו בסימטרי, כי זה סתם יהיה מכפלה סקלרית כזה.
אוקיי.
ואז זה בעבודה זה משהו שחיים התחיל לכתוב לפני כמה שנים, אז הוא ניסה, אז הוא אמר שבוא נניח ש-A ידוע ואני רוצה להסיק את B, B זה הפרמטר שאני רוצה להסיק. השאלה, אז אם יש לך השגות כלליות על הכיוון הזה, או האם הקורטקס זה אזור שהוא, כאילו, בכלל כל המושג הזה של סיבוב בתאים, אז כאילו, אז פיצ'ר וקטור כזה, מה יהיה הפיצ'רים שם? זה דברים גנטיים בסוף היה, ואם אתה רוצה גם להכניס נגיד את הפרמטר כאילו, אתה רוצה לדעת הסתברות ששני נוירונים אם יהיו קשורים, אז תכפיל את כל הפיצ'ר וקטור הזה סתם במרחק האוכלי, אם אתה רוצה לקחת חשבון במרחק. אז טוב, אני חושב שזו שיחה יותר ארוכה כמה דקות, אבל אם יש לך השגות כאילו ככה top of your head כזה, משהו ככה מעניין.
א', אני לא מכיר את המאמר הזה, אני יודע שיש, אתה יודע, אתה מכיר את אייל גל.
אייל גל?
שעובד עם... יש איזו סיטואציה מאוד מוזרה, שאני לא בדיוק מצליח לפענח אותה, אבל יש, אצל חיים יש את...
נכון,
אבל לא על זה הוא עובד על משהו קצת אחר, ממש על הריאליזציה עצמה.
נכון, אתה צודק, זה דומה, זה קצת השכונה של משהו.
כן, ואצל עידן, אמיר קרברדורגן, בחור אחר שקוראים לו אייל, שהוא עובד על... הוא בדיוק עכשיו מגיש את הפלזמה חמור, והוא עובד על כיוון, בוא נגיד בעבודה שלו, יש כיוונים משותפים לזה, בגלל שהוא עובד בעיקר על העניין של מוטיבים בתוך הרשת. זאת אומרת, אם יש קונקטור...
זהו, אז אני דווקא מתעניין רק בסטטיסטיקה של כל הרשת.
לא, אבל הוא מתעסק כאילו על higher order statistics. פחות כאילו על ה-first order.
כמו שניידמן.
שניידמן יכול, אני לא מכיר שהוא עובד על זה, עובד על זה גם?
פעם אחת שהוא הסביר לי משהו עושה פעם, higher order statistics.
לא, הוא עושה higher order statistics, אבל פייתון בעיקר, וכאן זה על הקונקטור. לדוגמה, כאילו, נניח שיש לך הסתברות של קשר בין נוירון פיצ'ר אחד לנוירון אחר, האם ייווצרו מעגלים שהוא קשור להוא, הוא קשור להוא, הוא קשור להוא. האם הם יהיו higher than chance?
כן, אתה רק מסתבך אותי, כאילו, זה כבר מסובך.
לא, זה מסובך, אבל קודם כל, המרקרים יש בעיה עם הדאטה, זאת הבעיה האמיתית בכל הדברים האלה זה בעיה עם הדאטה, כי כרגע עוד אין קונקטור.
נכון.
והקונקטור שיהיה, הוא לא יהיה גנטי בכלל. הוא יהיה מבוסס על עבודות של...
נכון, הגנטי אני רוצה, זה מה שאני רוצה למצוא, את הפיצ'ר וקטור.
חשבתי שאתה רוצה למצוא את ה...
גם את B אני רוצה, אבל הפיצ'ר וקטור זה ה-hidden variable שלי.
אבל הפיצ'ר וקטור באיזה הקשר, איך אתה תמצא אותם? אני לא מבין, כאילו מה, אתה צריך להמציא אותם בעצם, כי אתה לא יודע מה הפיצ'ר.
לא,
כל הגנום...
לא, ברור שלא. אז אני אגיד, אני אחיל איזה 10 גנים שנראים לי חשובים
על הקונקטיביטי.
כן, לא יודע, משהו.
ואז הפיצ'ר אומר לך כאילו מה רמת הביטוי של הגן הזה.
אני מניח שזה יהיה בינארי בתור התחלה.
אם יש לו או אין לו את הגן הזה?
הוא מופעל מעל איזה threshold, אם הוא... זה נראה מאוד, הנה, הבי כבר בא לקלקל.
לא, אתה כאילו אומר, אני לוקח נוירונים פירמידליים, ואני לא יודע, כאילו יש להם גנום, יש כל הגנום שם, ואני לא יודע על איזה גנים הוא מסתכל, ואז מה? ואז אתה עושה... מה?
לא, פה זה הריאליזם של הקומפיוטר.
לא, אתה לא מבין מה קורה להם אחרי הקטע של הענבל דמי, אתה לא שם לב
ראיתי, כשהשעה התחילה, אתם יודעים, שיהיו פציעה.
אנחנו עושים את המחקר.
לא, בסדר גמור. רק היית צריכה להראות כמה A, T, T, G, G, G כאלה. איזה גן זה? A, A, G, G, G,
באמת יודע שאתה... וואלה, אני מסתכלת על זה.
מה, הרקע שלה?
פיזיקה קוראים לזה קארטים,
אהלן,
העבודה שלכם, כל אחד היה בעולם העבודה.
משם נתקענו
כולם
בזה.
היו? כולם עשיתם?
כן, אבל כולם קצת במעבדה.
אחד הדברים שלמשל היום מה שדומה להישמע אתה מודל של סטטי עכשיו לוקחים נוירונים, שמים אותם שכל פעם כשהם מתחילים אחד לשני הכל שזה כזה צמריות וזה בוא נשים סטטי מזה זה יכול להגיד
אם מישהו לא קורא את סוף שלי, תסתכל על הדאטה
לשאול כל מיני שאלות
לא אין לי מושג מזה, אין לי מושג מזה,
איך אתה יוצא אתה יודע שאומרים אותם
הייתי כל כך נמוך, אמרתי לך, אני
נקוד בסיפור שאני מבחינתי נניח שנתת לי אבל אתה אומר שיש לך לראות אבל מה אתה מנסה לעשות?
לא, בכלל ממש כאילו, נשמע כאילו הכירו חוזר בכל תחתון של צבא, אבל אין לי מושג בזה.
לא,
תתחיל לעשות את זה. לא ביקשתי, לא תשמע, אני לא מכיר את זה באמת, לא כל כך
למשל האם כאילו במאמר הזה
אבל הייתי יכול לדבר, הייתי יכול לדבר. מה? אתה רוצה להגיד בעצמם? בגלל שאני כבר התחלתי לדבר איתו נורמלית, יצאתי בסיפורים לו. לא דחת. הייתי כבר באמצע, לא יכולתי להגיד.
זה עדיין לא יכול לעשות
זה או של אחד, לא חשוב, זה עושים איזה סקיילינג של ל-CAD ואז עכשיו CAD כאילו מכפילים את זה ב-N כדי שזה יהיה או של אחד ואז במודל הזה CAB הוא רק כאילו אחד משני הרכים כאילו C-in או C-out כאילו רק האם זה דוח לייבלי או בין לייבלי אז זה מאוד מתקשר, כאילו כבר זה נורא קשה, זה נורא מתקשר, כאילו רק זה מאוד לא ריאלי, כאילו הייתי רוצה שלכל זוג יהיה לפי שלום, זה כבר הרבה פעמים זה מאוד קשה, זה בעיה, פירמידלי, יש לך כן, אז דיפוטורים אחת לשנייה, זה נורא נמוכה, יש לנו מופרע. אז בגלל זה הרבה אנשים מתעסקים בעיקר בקיצור,
I have just a short announcement. So we are back after a very long vacation time, and I think it's going to be fragmented also in the future. It's not going to be smooth till the end, but basically I'm taking over, I think, this Wednesday and doing olfaction and audition, and there's still one last slot where we have Neil and Dan that are giving a lecture. So if the rest of the people who are not from the computational program, if you have a crave to give a lecture instead of a short paper, contact me and we'll give you a paper to present instead of the paper to write. Otherwise, we will have another paper to discuss. Okay, so basically we'll give a paper to all the class, just like we did the Yubel and Weasel one, and we'll take something that will be part of the exam as well. What? So you need a volunteer, yeah. That's it, I think. Okay, and the papers, yeah, the olfactory people have their papers, right? All of them? And the auditory, I will give, I will think about it this week, and bon. And I'll pass on attendance sheet.
Please write my name because I won't be able to.
Don't worry, you are part of the attendance.
So, hello, good afternoon. The paper I am about to present is the representation of social facial touch in real visual cortex, not in here which is the unsocial touch. First, some motivation.
about why they conducted the study at all. Most of the information we have about the visual cortex is from artificial movements or very controlled movements of the whiskers. You're all familiar more or less with the visual cortex and now which neuron corresponds to a primary whisker whose movement it represents in its activity. But we don't know much about naturally occurring scenarios in which the visual cortex is participating, and specifically social interactions or social facial touch in this example. And this paper is a very interesting paper which researchers studied this very new exciting field. Now, because this is a very new field, we don't have enough data about it, so we can enough to ask any specific questions. Because of this, this paper isn't an hypothesis answering paper, meaning it doesn't have a specific research question, but it's an exploratory paper. They said we can prepare a paradigm, a behavioral paradigm, in order to study the activity of the behavior and activity of the rest and the visual cortex and see what happens. And this is the paper I'm going to present. So, we are speaking about the visual cortex. The visual cortex is around here at the somatory sensory cortex. Here it's around layer 4, but also a bit 3 and 5. It receives direct input from the thalamus, among others, and indirect input from the brainstem and the whiskers. You're familiar with that each barrel in the visual cortex corresponds more or less to a primary whisker. This area is relatively easy to study because it is close to the surface and the very familiar way each neuron responds to a specific whisker. So because we know enough about the components that are composing the activity of neurons by artificial movement, we can now study the more free, natural occurring whisking behavior. In order to study this, the researchers prepared a behavioral paradigm in which the subject rat was sitting or standing or something on an elevated platform in a Faraday cage. When on the other elevated platform were the stimuli, which were separated by a wall. So the subject rat could interact with the stimuli rats or objects, but the stimuli could not interact with one another. The stimuli were female rats, male rats, and different objects, which range from toilet paper rolls or plastic bottles or other objects, which the paper didn't state. The subject rat was able to freely roam around the platform as the stimuli rat could also, and they interacted above the gap. In the trails where either the subject rat or the stimulus rat jumped over or moved over the gap, those trails were discarded. So all data is only from facial whisker touch, which is a very smart paradigm, I think, because this way they can see natural social behavior, but in a very controlled parameters, only whisker and nose touch. Okay, moving on. New stimuli were presented each block. Each block was more or less 10 meters. Now, the parameters that the researchers used were both behavior using videography and neural activity using electrophysiology. In the videography, the researchers using high-speed cameras, they recorded the angle of the whisker, the amplitude of the whisking behavior, the nose-to-nose distance, and generally the location of the subject rat and stimulus rat noses, and the time parameters, which are the onset of the first whisker overlap, which signifies the start of the interaction, the last whisker overlap, which signifies the end of an interaction. Interactions were more or less discrete units of the interaction, social touch, and nose-to-nose contact, which was important, apparently. In the electrophysiology part, they only used the information of spikes, of the timing of spikes, and from that they made the mean, calculated the mean fairing rate of the cells and a raster plot of the interactions. Okay, so yeah.
Is it okay?
Yes, sir.
I'm probably jumping ahead of myself, but did they check
You
at
can
all
help.
with my left foot?
Left foot.
Did they check at all uses of odors or scents that they've been studying?
No, and it's a criticism. Very good criticism, but a very good point. But no, they did not in this experiment. So these are the parameters that they used, and even though they didn't use the sense or sound, they got to very interesting results from these parameters alone, which I think is worth mentioning.
I have a question.
Yes.
Maybe it's a dumb question, but
There are no sense.
do rats have facial expressions? Like maybe they can interact by
I think
faces?
so, but I didn't. But they sorry. I think so, but in this case they were infrared light, so the rats could not see.
Hmm.
So even if so, it wasn't presented. Okay, so the results.
Yeah.
Okay. So the results. So we studied the social facial touch. In this figure, I'll explain it. The x-axis is 0 is the start of the interaction, the first whisker overlap, and these are milliseconds before and after interaction. These are the angles. This is the angle of the whisker of the subject thread. This is the angle of the whisker of the stimulus thread, and this is the nose-to-nose distance between the two reds. This is the firing rate of the cell, and these are the interactions. These three figures are from recordings of a single cell in layer 5B in a single breath, obviously. And as we can see, before interaction, whisker movements were more or less regular, moving from one angle to another, but from the interaction, as soon as 200 milliseconds after first whisker overlap, the movements became very irregular with low amplitude. This happened as nose-to-nose distance decreased, and when it decreased enough, the cells started to fail. These are spikes. You can see this interaction here in the raster plot, where there are 3 spikes. In the average of the fairing rate, you see that during all interactions, also you can see it here, the cell failed more as the nose-to-nose distance decreased. But why do I emphasize about the nose? Because of this. Here you can see the occupancy and fairing map, meaning, and I'll explain this. This is the snout of the subject rat, and each point in these figures, in this map, corresponds to the peak of the nose of the stimulus rat. Okay, meaning that each point is a place that the stimulus rat was in relation to the substrate during all interactions. And as you can see here, even though the nose of the stimulus rat was all over the place, during most interactions, it stayed mainly around the nose of the subject rat, which you can say okay, it's a pattern, a behavioral pattern of social touch, but as you can see here, this is a fairing rate, a fairing map of the whisker cells, of the visual cortex cells, normalized by occupancy. And as you can see, the whisker cells, the visual cortex cells, failed more when the noses of the two rats touched. This is very interesting because these are whisker cells. They are not nose cells. Okay? There is no trivial reason why the cells would fire more when the nose are with spatial proximity. And again, it's normalized. You can say that this is because the rat simply stayed in this location longer.
Just a question.
Yeah, sure.
Couldn't, when the nose both rats touch each other, couldn't more whiskers touch as
It's
well?
a very good point. I think so also. the paper mentions this, and let me rephrase your question, or your note. What you're saying is that this can be explained simply by the social behavioral pattern. Maybe when they are touching, more whiskers are touching each other. It could be. So let's move on. In order to answer this question, the researchers try to divide the data to explain the data further. If we until now we studied social touch, social interaction, we want to study unsocial interaction, but because we can't use unsocial rats, we use non-animate stimuli. And because we don't want to use the entire animal kingdom as stimuli, we use only the rat stimulus and not the non-rat stimulus. So now we divide the conditions between objects and rats stimuli. The subject is rat, of course. Yes, please.
Maybe jumping ahead, but did they have toy rats?
Sorry?
Did they use toy rats?
It's another great question. No, it's another criticism which I'll come to next. You're asking some good questions. So in this condition, there was interaction between subject rat and stimulus rat or different objects. Okay, and you're familiar with this kind of figure already. Only that note that now it starts with the beginning of the interaction, not before and after. And as we saw earlier, the behavior of the social interaction, the whisking behavior at social interaction is very irregular, with small amplitude changes during among the youngers. But in object interaction, on the other hand, there was very regular amplitude changes and the angle changes. A very regular whisking behavior as the nose-to-nose distance decreased. Even more interesting is that the 40% of the cells that were recorded reacted more to social interaction than to object interaction. This is a very interesting result because we can't say it because we can't predict it just from this behavioral pattern. Yes.
What is the nose-to-nose
distance
with the object?
Nose to object distance.
Just any.
Yes.
Were all object stimuli stationary?
Yes, they were all stationary and all perturbing to the middle of the gap. So rats could interact with them.
So they didn't check non-animate but still moving the disc?
Okay. So, but still we can. So this is an interesting result. But still we can explain it by different behavioral pattern of whisking. We can. So we will stay in the. So because we can't really disregard this hypothesis, this explanation, we will stay in the social condition and try to find the differences just in this condition. So how can we further divide the data? How can we explain social interactions by the best parameter? And these are rats, these are animals, alive animals. So they use gender. We will use gender. There are male rats and female rats, male subjects and female subjects, and male stimulus and female stimulus, which the researchers thought can explain is important for social interactions, and because of that might cause a difference in the neural activity. So we have male female, female male, and female interactions. And the results were as follows. The male and male stimulus responses, in male and male female conditions, the cells were very modulated by the different conditions, meaning at the baseline, not during social interactions, the cell fired around this firing length, about 2.33 Hz. But during interactions, male firing rate increased by 44% to 3.35 Hz. On the other hand, for female subjects, the increase was much lower, 19%. Now, this, I think, is the most interesting result of this paper, because the researchers try to decode from the behavioral parameters alone which condition this interaction belongs to, and they didn't succeed. Meaning, you can't see only from the whisking behavior if this is a male-male, male-female, female-male, or female-female condition. Meaning, these results cannot be explained by the whisking behavior. They must be, they have to be the result of a higher up, top-down modulation from other senses to the visual cortex. And I think this is the best result of this paper. Having said that, as you can see, the male baseline increased from 2.33 to 3.35. This is a 44% increase. The female increased from 3.14 hertz to 3.73 hertz. It's a small increase, but it's higher. It's a higher firing rate both for the baseline and for the interaction. The paper didn't say if this difference was significant, although it was higher than the male firing rate. And I think it's interesting to note. This result is important, nevertheless. Okay, so now that we saw how we can explain the data, we want to explain the data further. So why is gender condition? Yes.
Did they control for ichum of the?
It's an excellent question. They did. They when animal condition.
Animals in heat.
Animals in heat. They did. They controlled for female, estrous female subjects and non-estrous female subjects, and to try to see what the different response this will lead to. And it did lead to very interesting differences. As you can see, non-estrous females, okay, this is the excitation in interaction compared to excitation firing rate compared to baseline firing rate, spontaneous firing rate, okay? So, non-estrous females, when interacting both with male and female stimulus threats, increase their firing rate more or less the same, not in a significant difference. But estrous females, when interacting with other females, decreased their firing rate, inhibited their firing rate. Let that sink in for a moment, okay? What these results tell us, that estrous female rat subjects, when interacting with other females, their barrel cortex cells produced less spikes than the spontaneous activity, not during any whisper touch. Okay? This is very, very interesting, suspiciously interesting, in my opinion, but this is the result that they got. Now, you're probably wondering if estrous female responses change so dramatically between male and female stimuli, what will be the male responses to the difference in male responses to estrous and non-estrous female stimuli? Because I would presume, at least, that that this information is important for me. But unfortunately, we don't know that. The data was divided until this division, until this condition, and wasn't divided further to the estrous female stimuli, to the estrous and non-estrous female stimuli, only to the estrous and non-estrous female subjects. So.
Yes. Can I go one? Are these like paired tests or unpaired? So I mean, these are tetrads, so they can actually follow the same female a long time. So is it like within subject or kind of overall over the whole population?
I believe it was overall. They didn't mention, but from the web I can say it's overall. Okay, so to conclude the major findings of this paper, the ones that I chose to present at least. 40% of recorded barrel cortex neurons were modulated by objects and social conditions. This is an interesting finding, but as Nimrod mentioned, it can be explained also by different behavioral patterns, different behavioral whisking. So it's interesting, but can be explained by known parameters. Spatial proximity increased social interaction firing rate. What we saw in the occupancy map and when the nodes have increased, to node distance increased. This is also interesting because why would the cells react to node distance instead of to whisker touch? And this is another interesting result, but again can be explained maybe by behavioral parameters. Maybe during social touch, all of the whiskers are engaged the most when the nodes are touching in social facial touch, compared to object touch. So it's a strong result, but still can be explained by known data. But subject and stimulus, gender and sexual conditions modulated neural activity with the same behavioral parameters. As I mentioned earlier, this I think is the most important result of this paper, because this tells us that the visual cortex is modulated by higher up top-down mechanisms and information, probably arriving from the thalamus, but they didn't mention it, so I won't either. Okay, these are the findings. This article, being an exploratory article, didn't answer questions but raised questions, which is okay. And indeed it raised many kinds of questions. Some of them you already asked yourself. Did objects and social difference was objects and social difference based on shape, with a doll shape, like Lily said, I believe, a red-shaped doll? Was it based on scent or on sound? Was gender and estrous cycle difference based on scent or sound? How did they know? What was the gender and sexual condition? Is the firing rate averaged over all whiskers, or only those engaged in both object and social touch? Because if it was averaged over all whiskers, we can explain the 40% higher firing rate of the social touch simply by the fact that more whiskers were engaged in social touch. But if they only used those whiskers that touched, that were engaged in the behavior, and still 40% of the neurons reacted more to social touch, this is more interesting. And I believe this is the case, but they didn't mention it. What do the different firing rates signify? Is it sensitivity? Is it the interest of the input? What is the meaning of the increase or decrease of the firing rate during social interaction? Why is male baseline lower? Why is female firing rate higher than the male even during interaction? Why, as we saw in the male-female subject condition, we saw that the female baseline and interaction firing rate is higher than the male. Is it statistically significant? Is this difference perhaps pronounced also in object touch? What does it mean? Are females more sensitive in the overall, only more sensitive in the social context? Is it coincidental? We don't know. What does the estrous female inhibition of other females signify? This is a very surprising result after all. Why would females be less sensitive to other females, even from if it's really sensitivity? Why would they inhibit the responses of the visual cortex? And finally, the most frustrating. This is frustrating. The question that caused most frustration: how do male visual cortex cells respond to estrous females? I wish to know this information. Now, sorry, I take it very personally. Now, most of it, a good article gives rise to many different questions. And most of these questions can be, maybe not a full PhD study, but many papers can be written about the questions that we now can ask only because of this paper, which is great. But almost half of these questions can be answered by the data from this paper itself. If the firing rate averaged over all whiskers is a data that the researchers do have. We don't have to conduct any new experiments in order to answer this question.
I'm not sure. Is it possible to know which whiskers they took part in this social
Yes,
relation?
I didn't mention it. They recorded the whisker movement, but they used the ultraviolet epoxy tagging in order to know precisely which whisker is moving. So they could know which whisker is touching which whisker. What's that your question?
Yeah,
No.
but I guess that they also could cut all the whiskers and that just
They did.
leaves one.
It's a very good question. They trimmed not only one, but they trimmed all of the whiskers and saw the difference. There wasn't any difference in the subject, in the non-trimmed rat. In the trimmed rat, there was no response. There were no responses at all. But this question we can answer from the data the researchers have. Is the male-female firing rate different? Is another question that we can answer from the data the researchers have. Is it pronounced in object touch? And the vernal cortex cells respond to the estrus signal is another question that the researchers don't need to conduct additional research, additional studies. The researchers have the data from about the estrus state of each female rat from 2 days prior to the experiment. It says all the supplementary data. So they do have this division of data. It might be that they didn't find any significant results, but I think if they can say that the males don't respond differently to estrus and non-estrus females, by itself is a very interesting result. And they didn't answer it. So to conclude, studying this paper for me left an aftertaste of curiosity, frustration, and criticism, which I think are the ingredients to further research. So the paper should give an applause just for that. Thank you. Any questions? Yes.
How much did they address the question whether the behavior is different in the different conditions? So did they describe any, I don't know, interaction time differences or any other behavioral parameter in the different?
They did discuss the behavioral differences in the social conditions, in social conditions between the different conditions, and they couldn't find any. Maybe there was a difference, but there wasn't an encoding difference for the different conditions. They couldn't find from the behavioral parameters which condition it was.
Okay.
It's not your question. What?
Okay.
It is.
Did they look at food or inanimate objects?
And they didn't mention all of the objects. They didn't specify which objects they used. They specified, I think not, because they said they used cardboard and plastic and other materials, and they didn't mention organic materials. So I don't think so. Thank you.
Well, have a nice day. Stand up, Shili Sudan.
כן, אתה רשום לדעתי.
רשמתי אותך.
Right.
סוף בילוי, אז וואי, זה נראה לי סרט סוף בילוי. כאילו וואי, הפרפורמנס פה הכי טוב. רגע, אתה מכין את כל הבדיקות האלה מראש, או שלא אתה במקום?
מהרגע לרגע.
לא, באמת? לא, אתה מכין אותם. אינגרידיאנטס או
ליאור, לאן?
יש לך אבל? אתה תכתוב את זה דווקא. כן, זה כאילו בקומה 5, כמו שאתה לך ברגלנו, ולפני כן יש לנו מקום כזה עם דלת שקופה כזו מסודר.
In my case, that's way more freaky than just killing. I mean, come on.
כאילו, אני כאילו לא משנה, או שנציג משהו, כאילו יום או שנציג יום שעשיתי, או שנציג מעבדה אחרת. אני לא כאילו את העניינים לא הייתי אבל בעצם כולנו,
I love animals.
את כאילו באמת חושבת כאילו, זאת אומרת, אני רוצה כאילו להגיד את תן לי עוד שבוע, אני אעשה עוד. ספציפית באמת בתקופה הזאת, השבוע לא יעזור לי, אבל כאילו באמת, פשוט אין מצב עכשיו שפה תגיד בשיטות, שתראי איזה דינמיקה, עוד יש הרצאה לכן שלא משנה מה הרצאה שלך לעבוד עליה, ויש הרצאה גדולה, זה לא בשביל יש מה לעבוד, כאילו אין, כאילו, אני אפילו רוצה באמת לבוא ומילים, זה בסדר שנציג מה שיש לנו, או שאנחנו קצת, כאילו, שזה שתי האלטרנטיבות שאני רוצה להציע, כי את מבינה בקטע של, כאילו קיבלנו מהמדינה